Okie doke, friends. So on this screencast, we're going to take a look at those same finite sums that we had been looking at. We're going to take a look at how to approximate the area under a curve, but then we're going to do it in such a way that we can well extend from the case of finitely many rectangles to the case of infinitely many rectangles, which, as we've talked about, is the ultimate goal. To do that, I got to do a little bit of vocabulary with you. I think you will enjoy some refreshers of high school vocabulary. If I were to throw this thing at you, you would dig deep into your high school memory banks and remember what that is. Well, that's what happens when we sub in 1 for k, and then we sub in 2 for k, and then we sub in 3 for k, and then we sub in 4 for k, and then we stop because that's a 4. And then we add all that up, and whatever it is, it is. Now, just so we're clear, there's that, and there's that. So I think you could say that this is also the sum of the two k's plus the sum of the k squareds. I think it's fair to say that if you have a sum of sums, you can write that as a sum of sums. I think that's fair to say. I think it's also fair to say that we could suck a 2 out of here and here and here and here, and so we could suck that 2 right out of the sum. It's fair to say that constant multiples can appear on either side of the summation. You could look at the summation as a semi-permeable membrane where constant multiples can pass back and forth. Variables cannot, but constant multiples can. Okay, so there are also some formulas of note. If I add up the first n integers, 1 through n, that's the sum as k goes from 1 to n of k. And you're just going to have to trust me on this because I'm not ready to prove it by induction with you. You get n times n plus 1 over 2. Go ahead, try it out in the privacy of your own home. Add up the numbers from 1 to 6. You get 6 times 7 over 2. Similarly, if you add up the first n perfect squares, if you add up the first n perfect squares, you get n times n plus 1 times 2n plus 1 over 6. Go ahead, add up the numbers from the perfect squares from 1 to 49, that's 7 squared. You will find out that that's 7 times 8 times 15 over 6. And if we were to add up the first n perfect cubes, add up the first n perfect cubes, you get n times n plus 1 over 2 quantity squared. Now, why on earth would I want to do this? Well, consider the following. Let's take that area under 10 minus x squared from 0 to 3. And instead of breaking that area up into 3 rectangles or 6 rectangles or 12 rectangles or whatever, what if we broke it up into n sub-intervals? N rectangles. Well, a couple of things would be very apparent. One is that each little width, each little delta x, would be the total length divided by the number of subintervals. Each little rectangle would have a width of 3 over n. The heights of the rectangles, we could do a right rectangular approximation method. No big deal here. We could do a right rectangular approximation method because it should be darn close to the left rectangular approximation method. where is the right endpoint? Well, the right endpoint here is at 3 over n, and this one's at 6 over n, and this one's at 9 over n, and this one's at 12 over n, and so on. And so it turns out that the nth right endpoint is at x equals 3, oh, I shouldn't use n, the kth right endpoint. The kth right endpoint is at x equals 3k divided by n. The first one is at 3 times 1 over n, the second one is at 3 times 2 over n, the third one is at 3 times 3 over n, and so on down the line. So, when I go to figure out the area is a sum of a bunch of areas. Bunch of areas of rectangles. There are n rectangles. And the height of each of them is determined by this function evaluated at that right endpoint. And the width of each rectangle is 3 over n. Now, I'm going to do a little bit of algebra because algebra happens to be one of our specialties. I'm going to distribute, that's 30 over n, minus, okay, 3k squared times 3, n squared times n. A little bit of algebra. So now the question is, what is this? Well, this is a difference of sums It's a difference of sums. And the question is, what is that? Well, this part, oh, let's use Magic Pen. Sorry, I'm going to interfere with your screen for a moment. Let's look at Magic Pen. What is that? Well, that is n copies of 30 over n. So I've got 30 over n plus 30 over n plus 30 over n plus 30 over n plus 30 over n, n times. You want to know what that is? That's 30. Now let's come over here. Well, what have I got? I've got a constant 27 over n cubed. Remember, n is the number of subintervals we use. That's a constant. And 27 is a constant, so that can pass right through the semi-permeable membrane. And that leaves me with the sum of the k squareds. Well, the previous slide said that the sum of the k squareds is n times n plus 1 times 2n plus 1 over 6. So now, if I want to break this up, if I want to break this region up into 28 rectangles, then the area that I would get would be this expression with 28 substituted. If I want to break this up into a billion subintervals, then I would just sub in a billion in all those places, and that would give me the area of all the rectangles added together. Now, this has a tremendous advantage. What happens as n gets large? Well, I got to go back to stuff we did at the beginning of the semester. As n gets large, the area is 30 minus, well, what's happening, back to Magic Pen, in here? Well, the numerator has an n cubed in it. In fact, it has 27 times n times n times 2n. This numerator is 54n cubed and some other stuff that doesn't matter. And this denominator is 6n cubed. So if I've got 54n cubed blah 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 over 6n cubed, that turns out to be, oh come on, help a guy out. That turns out to be 9. 54 divided by 6 is 9, and we can find out exactly what the area under the curve is. We can know it exactly. We're not guessing, we're not approximating, we know exactly what that area is. And if you were to look at our LRAMs and RAMs and MRAMs, you would see that those get closer and closer to 21. All right, one more. Let's look at the yo-yo. Y equals 8 minus x cubed on 0 to 2. And let's pretend that instead of breaking it up into 8 subintervals, we want to break it up into n subintervals. If we break it up into n subintervals, then this width right here, this delta x, is the total distance divided by the number of subintervals. And when we go to do a right rectangle approximation method, this height is determined by this function evaluated at that x value. Well, this x value is 2 over n, and this x value is 4 over n, and this x value is 6 over n, and that x value is 8 over n, and so on. So when I go to find area, I'm going to take the sum over n rectangles of 8 minus somebody cubed times the width of each subinterval. What's that somebody? Well, the first somebody is 2 over n, and the second somebody is 4 over n, and the third somebody is 6 over n. So this is 2k over n. And a little bit of algebra tells me that this becomes 16 over n minus 16k cubed over n to the fourth. Now, what happens to this? Well, this part is 16 over n, 16 over n, 16 over n, 16 over n, n times. That's not bad. This part is 16 over n to the fourth. That's a constant, that's a constant. This is the thing we have a formula for, and that's n squared, n plus 1 squared over 2 squared. So now, what happens as n gets large? As n gets large, this first part is 16. This second part is n to the fourth blah blah blah, n to the fourth. Those will drop out. The limit of that quotient is 1. And so I've got 16 over 4. That's 4. And the area turns out to be 12. And your LRAM was bigger than 12, and your RRAM was less than 12, and your MRAM was approximately 12, and so that gives us some confidence that we're on a good track. Okay, so this is just a formalization of our process that I hope will be helpful to you as we move forward. Okay, thanks. See ya.